In the next few videos, we will look at methods to solve boundary value problems. Boundary value problems have been introduced to you already. We also looked at the corresponding MATLAB built-in functions, namely BVP init and BVP4C, that helps us to solve boundary value problems. What we are really going to look at here is what happens underneath BVP4C. So let's start with a few examples, and then I will outline the general technique, and then we will formulate problems for a few case studies, and then conclude with a few MATLAB files that use the built-in function BVP init and BVP4C. Let's look at a few boundary value problems before we proceed further. The first example comes from modeling heat transfer through a fin with constant cross-sectional area. We have looked at this equation before. Now, this is the second order derivative with psi being the independent variable and theta being the dependent variable. Here, there are system parameters that correspond to convective heat transfer coefficient, conductive heat transfer coefficient, the area over which the heat transfer occurs, the length of the fin, the perimeter of the fin, etc. So all of these are assumed to be constants. Therefore, this HPL squared by Ka term is a constant one. Therefore, this second term represents a linear term with constant coefficient. So overall, it is a second order ODE. By now, we know that to solve a second order ODE, that means to get theta as a function of psi, whether analytically or numerically, you require two conditions to be provided. So the two conditions are given here. One condition is given at psi is equal to 0, and the other condition is given at psi is equal to 1. Therefore, this becomes a boundary value problem because the conditions required to solve the problem are given at two different locations of the independent variable. If this was an IVP, then you would have had conditions like theta at psi is equal to 0 is some value which is given, and d theta by d psi at psi is equal to 0 will be also provided to us. Those would have been the two conditions which would have made it a IVP. Now here the conditions are such that one is provided at psi is equal to 0 and the other is provided at psi is equal to 1. So this is an example of a boundary value problem. As a second example, we are still considering heat transfer through a fin, but this time the fin has a variable cross-sectional area. Graphically, it's depicted here. This is heat transfer without any fin. So there is a surface that separates fluid 1 and fluid 2, and heat flows from fluid 1 to fluid 2. So this is heat transfer through a surface without any fins. Here we have these fins which are meant to enhance heat transfer by providing extra area for heat to be transferred. So in this particular case, we have cylindrical fins, and cylindrical fins have constant cross-sectional area. So this would relate to the previous example that we looked at. In this particular case, an example of variable cross-sectional area fin would be if we had conical fins like what is depicted here. So this is a fin, this is another fin, and as you can see, the area of cross-section of the fin changes from its base to its tip. This was not the case with a cylindrical fin, where the cross-sectional area of the fin remained the same throughout the length of the fin. Here, the area is maximum at the base of the fin and the area is minimum at the tip of the fin. So if you model this, you will get an ODE of this type. Now please note that this is a constant and A is a function of psi, the independent variable, and this term, which is the coefficient of d theta by d psi, is also a function of the independent variable psi. And all the terms are linear, right? So we have a function with independent variable psi multiplying d2 theta by d psi squared. We have a function of psi, which is the independent variable, multiplying d theta by d psi. And then we have a constant multiplying theta. So all of these terms are linear, except that the coefficients of the second derivative and the first derivative are variable. That means they change with psi. So therefore, this would be a linear ODE with variable coefficients, a second order ODE. Again, we are interested in finding out theta as a function of psi, the dependent variable as a function of the independent variable over this range 0 to 1 for psi. 0 would be the base of the fin, 1 would be the tip of the fin. So the two conditions that are required are given like this. One condition is provided at psi is equal to 0 and the other condition is provided at psi is equal to 1. So this becomes a boundary value problem. And we are going to learn how to process these boundary value problems. What are the techniques that can be utilized to solve such boundary value problems? We already know about BVP4C and BVP init that can be used to solve this problem. But here we are going to see how exactly BVP4C formulates and solves the problem. As you can see, if A is not a function of psi, if A is a constant, then we can replace A of psi with just A, a constant A. If A is constant, it is not a function of psi, then dA by d psi will be equal to 0. If A is no longer a function of psi, that means constant cross-sectional area. So this will be 0, so the second term will vanish and this term will remain as such. So I can bring A from here all the way to the bottom here. That means divide the whole expression by A and you will recover this equation. So this is a more general case where the fin can have variable cross-sectional area. In the limit, we have a regular fin with constant cross-sectional area. This equation would reduce to the simpler form that you see here. The third example is one where a second order reaction takes place in an isothermal tubular reactor with axial mixing. So this means it is not a plug flow reactor because there are diffusion effects. That's what leads to axial mixing. So diffusion is going to be dominant. There is going to be a second order reaction. So there is reaction happening in the system and there is flow that's happening, right? So there is flow from the reactor entrance to the reactor exit. So there is a convective term. So this axial mixing means we are going to allow for diffusion to take place in the axial direction. That means in the direction of fluid flow. Then there is a convective mechanism which transports the material from the reactor entrance to the reactor exit. That's the bulk flow. And on top of this bulk flow, you have these diffusion effects adding on to that. So the diffusion is quantified by this term. The convective flow is modeled by this term. And then the reaction is modeled by this term. Since it's a second order reaction, you have this dAy squared. This Peclet number relates to the diffusion. This dA is called the Damkohler number, which relates to the reaction. So these are things you will learn in either a fluid mechanics course or a heat transfer course or a reaction engineering course. In any case, if you have a second order reaction taking place in an isothermal tubular reactor with axial mixing, you do the mass balance equation, you will get this ODE. So it's a second order ODE because the highest derivative is of second order, and it is non-linear because of this term. Other terms are linear. This is a non-linear term because we have y squared, right? Y is the dependent variable and y squared will make this term non-linear, rendering the whole ODE non-linear. So here we are interested in finding out y as a function of x. Y is the dependent variable and x is the independent variable, and the reactor length is scaled such that x goes from 0 to 1. So x may be a dimensionless reactor length. So two conditions are required to solve this problem because it is a second order ODE. So one condition is given at x is equal to 0. The other condition is given at x is equal to 1. So this is a boundary value problem. So the ordinary differential equation is the same. In the case of an IVP or a BVP, the ODE doesn't change because that ODE comes from mass balance, assuming certain phenomena happening, etc. So there is nothing in the ODE that can tell us whether it is an initial value problem or a boundary value problem. Actually, you have to look at the conditions given to solve the ODE. And because the conditions are at different values of the independent variable, then we would say this is a BVP. Now, the difference between these three examples is, in the first case, the boundary conditions were simple, right? Both the boundary conditions are simply what is the value of theta at psi is equal to 0, what's the value of theta at psi is equal to 1. So very simple. In the second example, one boundary condition was simple, the other boundary condition was in terms of the derivative. So it appears to be slightly complicated. Now in the third case, both the boundary conditions are in terms of derivatives. And this one particularly looks a bit more complicated. So the question is, how do we deal with these kinds of boundary conditions? And we will see that the answer is very simple if we use finite differences and if we learn a few ways of dealing with it, a few tricks, if you can say that. We will get there ultimately. But as of now, we can keep in mind that because we are solving these ordinary differential equations, these boundary value problems numerically, we are going to be able to get the values of y at certain specific locations of x in this case, right? For example, at x is equal to 0.1, x is equal to 0.2, etc., depending on our step size or grid size. We will not be able to get an analytical solution of y as a function of x. We will not get an equation that relates y to x. So let's keep that in mind. Whenever we go for numerical solutions, we are not going to get an equation for an answer. We are going to get a sequence of numbers, and that is enough for many practical applications. Before I end this video segment, I just want to point out that there are many ways of solving boundary value problems. What we will focus on in this course is the finite difference methods, wherein we will replace derivatives, the first order derivatives, the second order derivatives, etc., by their algebraic equivalents using the finite difference approximations that we learnt earlier. Once we do that, we are going to get a system of equations that represents the ODE and the boundary conditions. If the system of equations happens to be linear, then we know we can solve it by LU decomposition or iterative techniques or simply using MATLAB's / command. If the system of equations is nonlinear because the boundary conditions are nonlinear or the ODE itself is nonlinear, which is often the case, then we will resort to solving the system of equations using Newton method. One other popular technique is the shooting method, where we assume values for the unknown initial conditions. Some conditions will be given at x is equal to 0 or t is equal to 0, right? So we have them, but we can assume some conditions at t is equal to 0 that are not given. Then what we do is we will solve the problem as an IVP, because once you have assumed some unknown initial conditions, the ODE becomes an initial value problem. So I can solve the IVP using ODE 45 or ODE 15s in MATLAB. Then what I'll do is I'll check if the solution obtained at the other end of the boundary, that means that x is equal to xf or t is equal to tf, meets the boundary condition stated in the problem. This means I have assumed the right values for the unknown initial conditions and the problem has been solved correctly. If the solution obtained at x is equal to xf or t is equal to tf does not meet the values stated in the problem, then I will reassume initial conditions and repeat this procedure until I make sure that the solution at the right boundary meets the conditions stated in the problem. For example, let's take this. Now, this is a BVP because one condition is given at psi is equal to 0, another condition is given at psi is equal to 1. What I'll pretend is I'll set this aside. How do I convert this problem into an IVP? If I can assume d theta by d psi at psi is equal to 0, I'm going to assume some value a. It's up to us to assume some value a. So this is what I mean when I say assume values for the unknown initial conditions. This condition has been given in the problem. We don't have to assume that. We require one more condition in order to make it a IVP. So I'm going to assume that d theta by d psi at psi is equal to 0 is some value a. So now with this assumed value of a, This conditions make it a initial value problem. Let's say I assumed A is equal to 0.5. So now it is an IVP. I will solve this set of equations using ODE for 5 and I'll get the solution. Theta as a function of psi. So it will be a bunch of numbers. For certain psi values, I'll get the values of theta. Let's say I use step size of 0.1. So at 0, it is 1 according to the initial condition. At 0.1, let's say some value is computed. 0.2, some value is computed all the way till at psi is equal to 1, some value is computed. Let's say it's a value r. This is the number. R is a value that was computed from assuming that d theta by d psi at psi is equal to 0 is a. Now I will check if this r is equal to 0 because that is what is given in the problem. Theta at psi is equal to 1 should be 0. That is what is the requirement if I've solved the problem correctly. If r is equal to 0, then bingo, I have assumed the right value of d theta by d psi at psi is equal to 0 correctly, and therefore this is the solution to the problem. Done. But if r turns out to be something different from 0, then I know my assumed value of a is not correct. It can be something smaller than 0.5 or something larger than 0.5. So I'll assume another value for a and I'll repeat this. And as you can imagine, people have worked out ways of correcting for this assumed value of a smartly. So this is in a sense the shooting method. You keep changing the values of a until this r meets the target, which is 0. So that's why it's called a shooting problem. If you apply the shooting method for this, again, I'll assume d theta by d psi at psi is equal to 0 to be, let's say, some value b. So I'll set this aside as a checkpoint. So now this is the ODE. These are the two conditions that can be used to solve the problem. So I will solve this using ODE for 5. Now I can get psi, theta and d theta by d psi, because this is going to be something like Z1 and this is going to be something like Z2, the two symbols that you use in formulating this problem for MATLAB. So anyway, you'll have for different values of psi, you will have values of theta and d theta by d psi. So let's say this is psi is equal to 0, theta is equal to 1 because that is one of the initial conditions. You have assumed the value of d theta by d psi to be b. So that will be the value. And then for 0.1, ODE 45 will compute these for you. For 0.2, you will have this until you reach a point where psi is equal to 1. You will have some value for theta and some value, let's say r, for d theta by d psi. According to the problem, this value r, which is d theta by d psi at psi is equal to 1, should be equal to 0. So I'll check if r is reasonably close to 0, within, let's say, 10 to the power of minus 8 or 10 to the power of minus 12. If yes, then my assumed value of b is right. So the problem is solved. If r is very different from 0, I will use a different value of b and I'll run the problem again. I'll solve the problem as an IVP again using ODE for 5. And I will repeat this process until I've assumed the right value of b, at which point this r will become 0. A similar idea for this problem. This I will set aside as a checkpoint. Here dy by dx at x is equal to 0 is known. So I'll assume a value for y at x is equal to 0. I'm going to assume a value c for it, let's say. So we have the ODE, we have the two initial conditions. Now I will solve this using ODE for 5. Then when I solve the problem, I will look for whether dy by dx at x is equal to 1 is 0. If it is 0, stop. Or sufficiently close to 0, stop. Otherwise, I'll go back here, change this value of c. And through that trial and error process, I will, at some point in time, reach a situation where dy by dx at x is equal to 1 is exactly 0. Then I'll say problem is solved and I can stop. So shooting method is something like this. To solve a boundary value problem, I will solve that problem as several initial value problems. And I will do it smartly so that I zone in on the right values of C in this example or B in this example or A in this example. How to do it smartly, people have worked out the details, etc. So that is how you solve the problem using shooting method. I hope these three statements now make sense to you. The other technique that I mentioned here is what is called method of weighted residuals, MWR. This method is quite elegant and powerful, but since we do not have time, I will not go into the details of that. But I'll just say that in this technique, what we do is we assume a form for the solution. So we are going to assume that the dependent variable is a function of the independent variable x via a relationship that is given like this. Here I've shown a third order polynomial, but you can assume a first order polynomial or a second order polynomial or a fifth order polynomial if you want. If you assume that the system's behavior is linear, then you might just have these two terms. If you think your system is very nonlinear, you may have a fifth order polynomial. So basically it depends on what you think is the relationship between y and x. So you assume some form, and that form has these unknown constants or parameters C0, C1, C2 and C3. You will determine the values for C0, C1, C2 and C3 through a matching process. So there is something called the collocation method. So you will have something called the collocation points at which you will force the assumed solution to match exactly with the ordinary differential equation. And via that process, you would be able to determine these constants. So that is what the method of weighted residuals is. If anybody wants to learn more about it, I'm happy to talk to you separately about it, or I can guide you to some resources. I'll stop this video by saying we are going to focus on finite difference methods because it capitalizes on the finite difference approximations that we have already learned. And also the finite difference methods are scalable to the numerical solutions of partial differential equations quite effortlessly. So when you learn how to solve partial differential equations numerically, you will find that the finite difference methods are very useful for you. Therefore, I've decided to focus your attention on finite difference methods. I'll describe the numerical solution of boundary value problems using finite difference methods in the few videos that are to follow. Thank you for your time.